Welcome to lecture 34. We are talking about temperature measuring instruments. In our previous lecture, we have started our discussion on liquid expansion thermometers, and specifically we talked about liquid in glass thermometer. We will talk about the other variants in today's class, which is liquid in metal thermometers. So, let us look at our classification. We have talked about bimetallic thermometers, which is based on solid expansion, and we are currently talking about liquid expansion thermometers. Liquid in glass thermometers we have covered in previous lecture. So, today we will talk about liquid in metal thermometer, also known as pressure thermometer. We will also talk about gas expansion thermometers, and under which we will talk about gas thermometers or constant volume gas thermometer and vapor pressure thermometer. So, that will complete our discussion on temperature measuring instruments based on thermal expansion methods. So, let us start with liquid in metal thermometers. The principle of operation is very much similar to liquid in glass thermometers. Liquid in metal thermometers are also known as pressure thermometers. There are two distinct disadvantages of liquid in glass thermometers. The glass is easily breakable, and the position of the thermometer for accurate temperature measurement is not always the best position for reading the scale of the thermometer. We have seen how to read the scale to avoid parallax error in previous lecture. Both of these disadvantages are overcome in liquid in metal thermometer, such as say mercury in steel thermometer. The principle of operation is same as liquid in glass thermometers, the thermal expansion of liquid. So, this is an image of liquid in metal thermometer, consists of a bulb and then a tube is attached to the bulb. The tube may be flexible and the other end of the tube is connected to a pressure sensitive element. The pressure sensitive element can be a Bourdon tube, maybe a C type Bourdon tube or a spiral Bourdon tube or a diaphragm gauge. So, commonly it is either a Bourdon tube or a diaphragm gauge. Now, this pointer and scale is attached to the tip of the Bourdon tube. Let us say the pressure spring we are using is Bourdon tube. So, the way it works is we will put this bulb into the medium whose temperature we are going to measure. This bulb, this capillary tube and the Bourdon tube are all filled with a sealing liquid such as an oil or a glycerin. Now, when this bulb is put into the medium whose temperature I am measuring, the bulb will receive thermal energy, the liquid will undergo a restricted thermal expansion, a pressure will be developed, that pressure will be transmitted through this capillary to the Bourdon tube. Now, it is same as applying pressure to a Bourdon tube. So, there will be deflection of the tip of the Bourdon tube. The tip deflection will depend on the amount of pressure that has built up, and the amount of pressure will depend on the temperature of the medium. So, the tip deflection is used to move this pointer against the scale, and the scale can be directly calibrated in terms of temperature units, from which you can get direct reading of the temperature. So, pressure thermometers or liquid in metal thermometers consist of a temperature sensitive bulb, this is the sensitive element, an interconnecting capillary tube, a pressure or volume sensitive device such as Bourdon tube, bellows or diaphragms, a device for indicating or recording a signal related to the measured temperature. So, once again you have the bulb. So, bulb is receiving this thermal energy, you have this capillary, the other end of the capillary a Bourdon tube is attached. So, this is a spiral Bourdon tube, one end of the Bourdon tube is fixed. So, there will be deflection of the other end to this Bourdon, to this tip of the Bourdon tube a pointer is attached which deflects against this scale, and we can get the reading directly after suitable calibration. Please note that the bulb is put to the medium whose temperature I am going to measure. This capillary is exposed to the surrounding temperature. Also, this entire part is put within a case, and this pressure spring or the Bourdon tube is subjected to the temperature of the case. Now, as we just discussed that this bulb will receive thermal energy from the medium and a pressure will be developed. But this capillary and this case, they have different temperatures, and these temperatures can also cause the change in volume of this capillary or this pressure spring. So, there will be some error due to ambient temperature, and we need to compensate for this error. So, how this temperature compensation can be achieved? The measured variable in a pressure thermometer is the total internal pressure. This pressure is the result of two factors, the temperature around the bulb and the ambient temperature around the rest of the system. That means, ambient temperature around the capillary, ambient temperature around the pressure spring or Bourdon tube. But we basically want then the pressure be a function of temperature around the bulb alone, so that I can get correct reading of the medium. But the pressure build up depends both on the temperature of the medium, which is the temperature around the bulb, and the ambient temperature around the capillary as well as the pressure spring. Long capillary tubes as long as 200 feet may be used for remote measurement. Then the temperature variations along the capillary and the pressure sensing device will be significant, and it will require compensation for the effect of ambient temperature. Now, there are two types of compensation, full compensation and case compensation. When the ambient temperature effects are compensated for both the capillary and the readout instrument, that means the Bourdon tubes, the Pointer scale, that part of the instrument, the design is called fully compensated. So, for fully compensated design, the effect of ambient temperature effects are compensated for the capillary as well as the Bourdon tube and the associated elements. So, how do you do it? So, this is the measuring element. You have this bulb, the capillary tube, and this is the pressure spring or Bourdon tube. Now, I take an exactly identical system or exactly identical element and connect them as shown. So, I basically have two pressure thermometers and they are connected in opposition. This one I call compensating system, and this is exposed to the surrounding medium only. It is not exposed to the medium whose temperature I am measuring. So, this is exposed to the surrounding only. So, the pressure that is built up here is based on the effect of ambient temperature only. The pressure that is built up here is based on the medium temperature as well as the ambient temperature. Now, since this and this are connected in opposition, the pointer deflection will be based on the effect of medium temperature only. The effect of ambient temperature will be cancelled out. The motion of the compensating system is due to effect of ambient temperature only and is subtracted from the total motion of the main system, resulting in an output dependent on only bulb temperature. Case compensation is partial compensation. When the capillary volume is very small relative to total volume of the system, it is possible to leave the capillary uncompensated. So, you compensate only for the pressure element. There is no need for capillary compensation. In case of full compensation, you compensate for capillary as well as for pressure spring. But in case of case compensation, you compensate only for the pressure spring, namely the Bourdon tube, and the capillary compensation is not required or is not achieved here. The capillary compensation may not be required when the volume of the capillary is small compared to the total volume of the system. That means the length of the capillary is not very large. So, what we do in case of compensation is we take the help of a bimetal. A suitably designed bimetallic strip is attached to the pressure element. Case compensation is provided by adding a bimetallic spring that generates a force nearly equal to the one caused by the changes in ambient temperature. So, we have attached a bimetallic spring here. You know that bimetal will also undergo thermal deflection. Bimetal will show deflection upon changes in temperature. Now, this bimetallic spring is so designed that the deflection in the bimetallic spring is equal and opposite to the additional deflection caused in this pressure element due to change in ambient temperature. Then it is possible to compensate for the effect of ambient temperature in the pressure spring, and this is how case compensation is achieved. So, here are some of the thermometer liquids used in pressure thermometer: mercury, xylene, ethyl alcohol, ethyl ether, toluene. The temperature ranges are indicated. Mercury thermometer can be used from -40 to 650 degrees Celsius, xylene can be used -40 to 400 degrees Celsius, and so on and so forth. Note that when you want to use mercury for as high as 650 degrees Celsius, you need to increase the pressure inside the thermometer bulb. That means, the mercury filling will be done at higher pressure, so that the boiling point of the mercury increases. So, the range can be extended beyond the normal boiling point only by filling the liquid at higher pressures. Most bulbs are made of stainless steel, which is relatively inert and will withstand high temperatures. The speed of response increases with increase of bulb diameter and tends to be the fastest with vapor or gas and the slowest with liquid filling. So, later on we will talk about gas filled thermometer or vapor filled thermometer. Now, we are talking about liquid filled thermometers. The speed of the response of vapor or gas filled thermometer is more than compared to liquid filled thermometers. Accuracy of liquid filled pressure thermometers is around plus minus 1 degree Celsius. Now, let us talk about gas expansion thermometer. So, looks very much similar to liquid in metal thermometer. The difference being, instead of liquid filling, we now have a suitable gas filling. Oftentimes nitrogen is used. So, gas thermometer is filled with a gas such as nitrogen at a pressure range of 1000 to 3350 kilopascal at room temperature. The device obeys the basic gas laws for a constant volume system, that is P by T is constant at a constant volume, or P1 by T1 equal to P2 by T2, and this gives a linear relationship between absolute temperature and pressure. So, basic principle is that pressure divided by temperature, absolute temperature, is constant for volume being constant. The operating principle for gas filled system is that in a perfect gas confined to a constant volume, the pressure is proportional to the absolute temperature. The error due to non-ideal nature of the gas is small, and the measurement of pressure can be used to indicate temperature. Nitrogen and helium are most commonly used filling gas. Gas filled systems approximate Church's law. Absolute pressure of a confined gas is proportional to its absolute temperature by keeping the bulb volume relatively large compared to the rest of the system. Gas thermometers has widest measurement range. The lower side of the range is determined by the critical temperature of the filling gas. Higher side of the range is determined by the temperature limits on the bulb material. You cannot exceed the temperature at which the bulb material will melt. Typical range is minus 268 to 760 degrees Celsius. Nitrogen reacts with the steel bulb at a temperature of 427 degrees Celsius. So, use helium for temperatures of 427 degrees Celsius or higher. The longer the capillary tube, the bigger the thermal bulb should be. Accuracy is about plus minus 1% of full scale. Calibration is linear. Now, let us talk about vapor pressure thermometer. Vapor pressure thermometer system is partially filled with liquid and vapor. The pressure of the vapor above the liquid depends on temperature of the liquid vapor interface. So, vapor pressure thermometer is also similar to liquid or gas filled thermometers, but there is some difference. In case of vapor pressure thermometer, the system is partially filled with liquid and vapor. The pressure of the vapor above the liquid depends on the temperature at the liquid vapor interface. If we increase the temperature, more liquid is evaporated and the pressure increases. If we decrease temperature, some amount of vapor will condense and the pressure will decrease. The change in pressure with change in temperature is substantial and can be used for measurement of temperature. So, the basic principle that is used is that you take a volatile liquid and the pressure will change with change in temperature. Because the liquid vapor equilibrium is a function of temperature at the liquid vapor interface only. So, this is a schematic of vapor pressure thermometer. We have the bulb. Inside we have taken a volatile liquid. and you have the liquid and vapor interface in the bulb. So, if temperature increases, some amount of liquid will be evaporated. So, the pressure will increase. So, the increased pressure will show increased deflection in this pressure spring, which will be read by this pointer and scale. If temperature is decreased, some amount of vapor will condense and the pressure will fall. So, that will also be indicated by movement of this pointer against the scale. So, it is the temperature that governs this vapor liquid equilibrium. So, vapor pressure being a function of temperature at the liquid vapor interface, we can measure the pressure to indicate the temperature at the liquid vapor interface. So, you must put this bulb in the medium whose temperature we are measuring and ensure that the liquid vapor interface exists within the bulb for the vapor pressure thermometer to work correctly. Volatile liquids used are methyl chloride, ethyl alcohol, ether, toluene, etc. The lowest operating temperature must be above the boiling point of the liquid and the maximum temperature is limited by the critical temperature of the liquid. So, lowest operating temperature must be above the boiling point of the liquid, otherwise there will not be any vapor liquid interface in the bulb, and the maximum temperature is limited by the critical temperature of the liquid. The response time of the system is slow, being of the order of 20 seconds, and this is similar to gas expansion thermometer. The temperature pressure characteristic of the thermometer is non-linear. So, the calibration will be non-linear. So, this is a typical vapor pressure versus temperature relationship for methyl chloride, and here the temperature vapor pressure relationships are given for a set of volatile liquids such as methyl chloride, butane, ether, methylene chloride, ethyl alcohol, etc. Note that this scale is logarithmic scale, and that is why the plots look linear, otherwise the relationship is non-linear. The sensitive element is the reservoir partially filled with a volatile liquid which is in thermodynamic equilibrium with its vapor. This is for a vapor pressure thermometer. So, for vapor pressure thermometer to work, liquid vapor interface must exist in the bulb. The arrangement shown in the figure ensures that volatile liquid surface is always in the bulb. You note that we take a non-volatile fluid here and then we take a volatile fluid. So, you have this interface between volatile liquid and the vapor. Here are some of the liquids in the vapor pressure thermometers along with their ranges. Note that the ranges are not very high on the higher side. Pressure is a logarithmic function of temperature, so the scale is non-linear. A typical relationship of vapor pressure with temperature is log P equal to A minus B by T. So, a non-linear relationship is indicated and a calibration curve will be nonlinear. Accuracy is about plus minus 1%. The vapor pressure thermometer does not need any ambient temperature compensation. This is a very important aspect of vapor pressure thermometer. The pressure in the system is determined only by the temperature at the free surface of the liquid. So, the vapor pressure is governed only by the temperature at the liquid vapor interface. Changes of temperature elsewhere in the system may cause an expansion or contraction of volume, but it is automatically compensated by establishing a new vapor pressure equilibrium at the liquid surface, thereby maintaining a constant pressure. So, we will stop our discussion on liquid expansion thermometers here.